Use conjugates to rationalize the denominator. Hey, do you remember this? Like if I had x plus 3 and I multiplied it by x plus 3, remember how you'd end up getting like x squared plus 6x plus 9? So like, that's way too many terms maybe. What if instead I had multiplied it by the opposite symbol? So instead of having 3x plus 3x, now this term goes away, and I just have x squared plus 9. And that's kind of cool because you end up with like these squared terms, and maybe if instead it was like x plus the square root of 3 times x minus the square root of 3, I guess I would get x squared. These middle terms would drop out as I FOIL this, and I'd have the square of these two guys, which would just be 3. Maybe remember that. That's kind of cool. I also said, well, how about this? Meaning, do you remember this as well? But I don't remember what I was going to mention. So you're going to be stuck wondering for the rest of your life what I had thought about saying there. And it's going to bother you forever. So we're going to use conjugates to rationalize a denominator. And if I look at this, this is bad news because you got a radical showing up in the denominator. Now these usually take a little bit more work to do. So I'm going to try to write these with a little bit more discipline than my other problems. Now, even though it looks more complicated, I can still just multiply this whole thing by something where I'm going to put the same exact value up top and down below. Now, you're probably not going to be like remembering the word conjugate for a test if you were to take it like a month from now and not keep practicing this. So this is going to be one you either want on a vocab card or you want to just constantly remind yourself what's going on. So the conjugate is something you end up just taking the exact same thing on the left and you end up taking the exact same thing on the right, but you add them for this problem. So the conjugate is going to be the opposite of what you see there. So like if you had A plus BI, its conjugate is going to be A minus BI. So I've multiplied this by 6 plus square root of 3 in the denominator, and I have to keep the numerator the exact same. Now as you get into these larger and larger problems, it's sort of your choice if you want to put parentheses around this, and it really kind of helps the parts stand apart so that maybe you see that this 2 is really right here, if you think of it that way. And it makes it kind of clear that everything being multiplied across is really happening accurately. So the other thing too is some of these end up requiring kind of complicated foiling or distributing problems. We're only multiplying, foiling out and getting 4 separate terms here, but it's possible that you'd end up multiplying something out and end up finding yourself with one of those more intense polynomials where you multiply across 4 or 5 values. But for this one, I think we can manage jumping right in. So I'm picturing this, but I'm not drawing this. 2 times 6 is 12. I'll skip a line, but only so that it's more clear. 2 times square root of 3 with the plus sign there is going to be plus 2 square root of 3. All of this will end up being over. Now we're foiling down here. The first gives me 36. The outer gives me 6 times the square root of 3. The inner gives me minus 6 times the square root of 3. Well, that's why we use the conjugate. And if we've chosen opposite symbols here and not made a mistake, those 2 middle terms will drop out. So I don't have to write anything. But then my outer and inner I'm done with. My last is going to be the square root of 3 times the square root of 3, which is just 3. Now, there's no negatives in the radicals or anything weird going on, So this minus hits this positive, and a minus times a positive gives us a minus. And if you look at this, it's kind of strange because suddenly you have a problem that has no radicals in the denominator. So 12 plus 2 square root of 3, that is not going to be 14 square root of 3. You can't combine those. This is almost as if I was saying 12 plus 2x. They are not like terms at all. Even though there's no variable or anything, the only thing I can rewrite here is 2 radical 3. And then in the denominator, I have 36 minus 3, which is 33. Now, let's pretend for a second that this ended up being 34. Then, like with those earlier problems you did in the last section, you could, cancel out half of that and turn this into 17. But I'm only pointing that out to remind you that sometimes there are additional steps when you do these problems. But as it is written here, this is totally fine. Your book might end up having something like 12 over 33 plus 2 radical 3 over 33. It's the same thing. They just broke it apart. Okay, I'm going to clear that one out, and we will do another problem together, and then make this third one. Problem 2. 3 over 2 plus the square root of 2. Now, first of all, we need to multiply this deal by its conjugate, and it's all about the denominator. You're really not even looking too much at the numerator, except to see if maybe something cancels out nicely. So I'm going to rewrite 2 minus the square root of 2. I'm changing to get the opposite sign. Now up top I'm going to write 2 minus square root of 2, so that we end up, keeping it that I'm really just multiplying the whole complicated looking fraction on the left by something with a value of just 1. Let's do some parentheses to make it more clear. And then I'm going to distribute that 3 in my numerator. Sometimes you don't want to do that. It ends up being something you just have to factor back out later. So 3 times 2 gave me 6. 3 times square root of 2 gave me minus 3 square root of 2. And then my first down below gives me 4. My outer and my inner cancel out. And then square root of 2 times the square root of 2 is 2. Now I have 6 minus 3 over the square root of 2, all over 4 minus 2, which is just 2. Now, although you could cancel 6 and 2 out, you can't cancel 3 and 2 out. So maybe your book might say 3 minus 3 square root of 2 over 2. But I'm going to keep that all as one fraction because that's what in my opinion, I think is more simplified. But it's debatable. Alright, I'm going to rewrite 3, and then I'll start it shortly after. But I'd like to see this be an on-your-own problem, where you give yourself time to figure it out before I start talking about it. So pause this video and try it now, because the answer will be up in 3, 2, 1. There's my answer. I think you can probably look it over without me walking through it. So I'm just going to put some parentheses around that business, and if you need to look at this longer, pause it, and I'll move on. So here's a summary of some of the concepts. For something to be in the most simple radical form, the following 3 conditions have to be met. No radicands have perfect square root factors other than 1. Now what this means is that if I take the square root of 32, I know I'm not done, because 16, which is a perfect square root factor of that can get pulled out. However, if I had something like 10, I can't pull out 9 or 4. The only thing I could pull out would be 1, and that would do me no good. The other thing, too, is no radicands contain fractions. So, like, if you see something written like this, that's also kind of considered not all right. And then lastly, no radicals appear in the denominator of a fraction. So if I had something like we just saw in the problems that came before the conjugate ones, as well as the conjugate ones, it's not okay to have a radical down here. You'd have to rationalize it, and if it was something more complicated, you'd have to multiply it by its conjugate. So here are the problems to do. It's a ton of these. So, take your time. See me if the word problems feel strange at all. So we'll work on some of those together. A lot of videos for these notes, and I think that there's some definitely new challenging concepts, and I want you to be doing a lot of trial and error to experiment with these.